Hello, everyone. Welcome to the final edition of Math 135 for the semester. You guys have been doing a great job, and I know it's been tough, but we are here and we're going to learn about our last hypothesis test. Remember that WebAssign is due on Monday. Okay, so today we're going to learn about the last of the two-sample test where we compare actually proportions of people. So, for example, do men and women have different opinions about avocado toast? Do they tend to have different theological views? These are the questions we can address through polling using difference of proportions. Sometimes you can get different samples, and it might look like there's a difference, but there might not be enough statistical evidence to suggest it strongly enough for our sake. So let's take a look and see what we're going to do today. So today is section 10.3, and we're going to talk about the required things you need to check off the list in order to do a two-sample test with difference of proportions. So there's a lot of lingo that goes on in this scenario. So since we're doing a difference of proportions, we have two different populations viewed as independent. So in the first population, we're going to be interested in the R1 successes out of N1 trials for population 1. And then that might be men, and the number of successes might be men who liked avocado toast. R2 is the number of successes in the N2 trials in population 2. So if we're comparing men in population 1 to women in population 2, N1 is the number of men we surveyed. N2 is the number of women we surveyed. R1 is the number of those men who liked avocado toast, and R2 is the number of women who liked avocado toast that we surveyed. So we need to calculate this quantity, P bar and Q bar, and we also have P1 hat and P2 hat. These are all the quantities we need to calculate in order to do such a hypothesis test. Unfortunately, this is going to require some work by hand. And then we have to verify the following 4 conditions hold. We need that each of these quantities is bigger than 5. Well, there's no time to plug the present. Let's run through the things we do, and then we will do an example. So the hypothesis test works just like any other. Our null hypothesis is always that the difference of the proportions is 0. Or in other words, the proportion of men who like avocado toast is the same as the proportion of women who like avocado toast. And then our alternate hypothesis might be that, well, maybe men like it less than women. Then that would be our alternate hypothesis. Maybe men like it more than women, in which case we would have a right tail test. In any case, the test statistic is computed this way. This is the standard normal. And then we'll use it to calculate the p-value and conclude our test and come up with our conclusion. So let's do an example and see what we can calculate. So researchers conducted 2 random samples, one 2002 and one 2009, and we want to know whether the proportion of people who support stem cell research increased from 2002 to 2009. So these are our 2 populations. So let's get a little pen here. Okay. So we have 2 populations, the people they surveyed in 2002 and the people they surveyed in 2009. In each case, they surveyed 1,500 people. I know it says 15,000 there, but it should actually say 1,500. So each of these samples had 1,500 people, and in 2002, 645 people reported supporting stem cell research, and in 2009, 870 people reported supporting stem cell research in the survey. So we want to find out whether the proportion of people who support stem cell research increased or not. So our null hypothesis is that, well, the difference in proportions is 0. And our H1 is that, well, we think proportion 2 is actually bigger than proportion 1. So the alternate hypothesis is that the difference of proportions is negative. So we have to calculate a lot of things. And the first thing we want to calculate is P bar and Q bar. So P bar is R1 plus R2 over N1 plus N2. That's 645 plus 870 over 1500 plus 1500. And this is about equal to, it's about equal to let me bring up my annotation again, 0.505 roughly. Okay, now let's take a look at Q bar. Q bar is 1 minus that. So that will be 0.495. So we have to verify certain things are true. We need to verify that P hat or P bar times R times N1 is bigger than 5, Q bar times N1 is bigger than 5, etc. So let's clear all these drawings and go over to the whiteboard. So thus far, we've deduced that R1 was equal to 645, N1 was equal to 1500, R2 was 870, and N2 was 1500. P bar was 0.505, and Q bar was 0.495. So let's calculate P bar times N1. That's 0.505 times 1500. And that's roughly equal to, let's find out here. It's about 757. And Q bar times N1 is 0.495 times 1500. And that will come out to be roughly, let's see, about 742. It's about 742, and we see that these are both bigger than 5. So we need to check that P bar times N2 is bigger than 5, which it is, and Q bar times N2 must be bigger than 5, and that's also true. So these 4 conditions are what we need in order to do this hypothesis test, and they're all true. So we can proceed with the hypothesis test. So what the hypothesis test tells us is that our z variable is P1 hat minus P2 hat over this expression. So we need to find out what P1 hat and P2 hat are. P1 hat is R1 over N1, and that came out to be 645 over 1500, and that's roughly equal to 0.43. And P2 hat is 870 over 1500, and that's equal to 0.58. So now it's time to calculate our test statistic z. So we plug in all of these numbers that we have calculated. And see what that's equal to. And we find out that's roughly equal to 8.21. Now, if we recall, oh wait, that was my mistake. I switched up two things. Let me do one quick correction. This was actually 0.43 minus 0.58. And this is negative 8.21. So now we have our standard normal curve. We have negative 8.21, and that area is our p-value. And we can compute that using Excel. So let's move on over to Excel. Okay, so we can do equals norm.s.distribution of negative 8.21, comma true, and we get a p-value that's very small. That's 15 zeros. So we get something that's roughly equal to the p-value is 1.15 times 10 to the negative 16th. That's obviously smaller than our alpha, which was 5%. So we conclude that the proportion of people who support stem cell research increased from 2002 to 2009. So we conclude that we're pretty confident of that because our p-value is just so small. All right, so that was one hypothesis test. So let's do one more to make sure we know how to do this. And this is a 1997 study, real study, where people were observed at the mall for about 10 seconds in public places. And they wanted to know whether people smiled during that randomly chosen 10-second interval. And here was our data. And we want to perform a hypothesis test to whether the proportion of men who smile in public is less than that of women. Okay, so let's go over to the whiteboard and work it out there. Okay, so we have two populations, and population 1 will be men. And population 2 is women. And we're looking at the proportion of people who smile. So the null hypothesis is that they smile the same in public, but the alternate hypothesis is that men smile less in public. That is, the proportion of men who smile in public minus the proportion of women who smile in public is negative. We found that the number of men who smiled in public was 3,269, and the total number of men they saw was this number. Came out to 7075. And the number of women they saw smiling in public was 4,471. And the number of women they saw total was 4,471 plus 4,278. In other words, the total number of women observed was equal to 8,749. Okay, so remember that in order to do the hypothesis test, we have to verify that P bar times N1 and Q bar times N1, P bar times N2, and Q bar times N2 are all bigger than 5. So we need to actually calculate what P bar is equal to. And it's R1 plus R2 over N1 plus N2. In other words, it's 3269 plus 4471 over 7075 plus 8749. And that's roughly equal to 0.489. And so Q bar is 1 minus P bar, which is 1 minus 0.489, so that's 0.511. Okay, so now we need to test that P bar times N1, which is 0.489 times 7075. Let's see what that's equal to. Q bar times N1 is 0.511 times 7075. P bar times N2 and then Q bar times N2. So we need to calculate these four quantities and make sure that they're all bigger than 5. And these come out to be roughly 3459, obviously bigger than 5. 3615, that's bigger than 5. 4278, that's bigger than 5. And 4470, that's bigger than 5. All right, so these are all bigger than 5. And so the next thing we need to calculate are P1 hat and P2 hat. So P1 hat is R1 over N1. That's the number of men who were smiling over the total number of men, which I think came out to be 7075. And P2 hat is the proportion of women who were smiling, which is 4471 over 8749. We're going to see what these are roughly equal to. So this comes out to be 0.462 and 0.511. Okay, so to calculate our test statistic, we do P1 hat minus P2 hat over the square root of P bar times Q bar over N1 plus P bar times Q bar over N2. And this comes out to 0.462 minus 0.511 over the square root of 0.489 times 0.511 over 7075 and 0.489 times 0.511 over 8749. And this comes out to be about negative 6.13. So here is our standard normal. Here is negative 6.13. It's a left tail test, so we need to find that p-value using Excel. So let's share Excel. So we can do equals norm.s.distribution of negative 6.13, comma true. And we get a p-value of about 4.39 times 10 to the negative 10th. Obviously less than 0.01. which is alpha. So we reject the null hypothesis, and we conclude that the proportion of men who smile in public is less than the proportion of women who smile in public. And we're very confident of that because our p-value was so small. So we are very confident that men smile in public less than women, but if you go back to your P1 hat and your P2 hat, you see that the men only smile about 5% less than the women. So this is one example of a case where the statistics are very clear. Men smile less than women. But one thing that hypothesis tests do not tell you is they do not tell you how different are these two percentages. What we're seeing here is they're definitely different, but women don't smile that much more than men. So that's always important to know, that although the p-value tells you how confident are you in your conclusion, it doesn't tell you how much more women smile in public more than men. It's probably about 5% more. All right, let me know if you have any questions. And remember, the web science due on Monday.